And today we are going to do the computation for ANOVA, that how the analysis of variance is executed, how the statistical procedure is performed. And you need to remember some key points, like you need to have a clear research question, that you need to put your research question that you're trying to address through analysis of variance. So you need to have a clear concept of the research question that you're trying to answer. And then you need to have a clear statement of null and alternate hypothesis against which you're running your test. And you need to check your data if it meets the requirements of ANOVA. And remember that what are the main requirements for ANOVA? That the observations, they should be independent. The measurement or response variable, it should be a continuous data. And the homogeneity of variances, that variances between the samples, they should be homogeneous. Sorry, not the variances between the samples, rather the variances of the samples, they should be homogeneous, right? And what is the other requirement of ANOVA? The data, the observations, they should have a normal distribution, right? So these are the requirements of ANOVA that we discussed previously. And then you do the ANOVA computation, right? You calculate the ANOVA, you perform different steps of ANOVA, and then you have your results. So you must be able to interpret your results according to your ANOVA calculations, in light of the research question that you asked and in light of the null and alternate hypothesis that you had stated. And remember these important steps or important parts of the ANOVA computation. So you have to calculate the sum of squares, you have to calculate the total sum of squares, between sum of squares and within sum of squares. And then you have to calculate the degrees of freedom, degree of freedom for total, degree of freedom for between, and degree of freedom for within. And you have to calculate the variance, and you have to calculate two variances, between samples variance and within samples variance. And then finally you have to calculate the F value, the comparison of variances through F test, and that is to tell the significance of difference between mean values. So this is the scheme of ANOVA, and this is how you're going to do your ANOVA computation. Now the hypothesis. So for the ANOVA computation, we have the general null hypothesis that samples are taken from normally distributed populations with equal means and variances. And the general alternate hypothesis is that samples are drawn from populations with equal variances and at least one population mean is different, right? So these are the null hypothesis and the alternate hypothesis. So here in both of these hypotheses, we are assuming the variances of the samples to be equal, right? That all the samples, they have equal variances. So a check for the homogeneity of variances is to be done before we do the computation for ANOVA, right? So a check for variances to be the same must be performed before performing the ANOVA. And then what you need to remember for the ANOVA computation is a formula for sum of squares. So this is the simple formula for the calculation of sum of squares. This is summation x square. X are the individual observations, and the x square means the square of the individual observations, and then you take their sum. And this is to be subtracted from a factor which is known as correction term, right? And what is this correction term? That you take the sum of the individual score of observations, and then you take the square of that sum. So summation x whole square divided by the number of observations. So you can see that these two factors are different. The summation x square and the summation x whole square, they are different values. So this is the formula for sum of squares that you need to remember for the ANOVA computation. And the results of ANOVA are presented in a table form, right? So in the table we have the source of variation, which are listed in rows. So the sources of variation, as we discussed, they are between samples variability, within samples variability, and when they are summed up, that becomes the total variability, right? So the sources of variation are between samples, within samples, and the total variability or the total variance. Then we calculate the sum of squares for each of these three. We calculate the total sum of squares, we calculate the within sum of squares, and we calculate the between sum of squares. And then in the next column we have to calculate their degrees of freedom. So we calculate the degree of freedom for between samples variance, for within samples variance, and for total variance. And then we calculate the variance. So we calculate variance for between samples and within samples, because as we saw in the graphs that we have to compare the between samples variance with within samples variance to find out if the mean values are significantly different from each other. So we are going to calculate the variances of these two factors. Then we calculate the F value, and this F value is different from the F value which is used before the ANOVA. So we are going to perform two types of the F tests in ANOVA. One is the F test which is performed before ANOVA to check the variances are equal or no, and the other F test that is actually the ANOVA test, right? So this F test is the actually the ANOVA test, and this is different from the F test which is performed before ANOVA. And then the last column has the probability, which is the probability of the F value that we calculate in the ANOVA, right? So this is how we present the results of ANOVA. Let's do an example here for the ANOVA computation. So the example is mean masses of starlings sampled from 4 different roosting places. And the nominal variable in this analysis are the roosting places which constitute the samples. So we have 4 categories in the nominal variable, which are actually the different roosting places. The red bead roosting place, and a roosting place from tree, roosting place from a large building with ledgers, and a roosting place which is a cliff. So we have 4 categories of the roosting places. And our measurement variable is 1, which is the mass of starlings. These are the observations. So how many number of observations are there in each of these 4 samples? We have 10 observations in each of these samples. Now we have our question here for the exercise, and the question is there any difference in mean masses of starlings between roosting places? So this is the question that we have to answer, right? So to answer this question, we have to suppose a null hypothesis. We have to propose an explanation. And the proposed null hypothesis is there is no difference in the mean mass of starlings between different roosting places. The alternate hypothesis is the mean mass of starlings of at least one roosting place is significantly different, right? So this is our null and alternate hypothesis for ANOVA in this case. So in the null hypothesis, as usual, we're assuming that the mean differences are non-significant and their mean values are same. The mean mass of starlings at all of these 4 locations is same. But in the alternate hypothesis, we are not saying that all of these places are different from each other, the mean values are different from each other. We are saying that the mean mass of starlings of at least one place is significantly different, right? So this is the alternate hypothesis that we have here. Alright, so let's start the analysis. So here we have the table by which we can calculate our descriptive statistics. So here you can see that we have calculated the values of summation x and summation x square. So summation x is the sum of all the individual observations in a sample. Like in the first column we have 78 plus 88 plus 87 and so on, and the summation x is 836. Then for the sample number 2 we have 78 plus 78 plus 83 plus 81, and the summation x is 794. Then for the sample number 3 we have 79 plus 73 plus 79 plus 75 and so on, and the summation x is 786. Then for sample number 4 we have 77 plus 79 plus 75 plus 70 and so on, and the summation x is 754. And the other columns, they are about the x square values, right? So 6084 in the second column is the square of 78, and then the square of 88 is 7744 and so on. So we take the square values of all the individual values, and then we take the sum of these individual square values, and that sum is the summation x square, which in this case, in the case of first sample, is 70,036. Then for sample number 2, we have the summation x square as 63,100. Then for the sample number 3, we have 61,878. And then for the sample number 4, we have 57,006. So this is how we calculate the summation x and summation x square. Now we have the descriptive statistics table, and in this table you can see that the number of observations in sample 1 are 10, and these are 10 in sample number 2, 3, and 4 as well. So the total number of observations that we have are 40. Now the mean mass of starlings in sample number 1 is 83.6 grams. The mean mass of starlings in sample number 2 is 79.4 grams. The mean mass of starlings in sample number 3 is 78.6 grams. And the mean mass of starlings in sample number 4 is 75.4 grams. Then the variances. The variance in sample number 1 is 16.27 grams. The variance in sample number 2 is 6.25 grams. The variance in sample number 3 is 10.96 grams. And the variance in sample number 4 is 17.14 grams. Then we have the summation x values that we calculated from the previous table. This is 836 for sample number 1, 794 for sample number 2, 786 for sample number 3, and 754 for sample number 4. And the total is 3,170. And then we have the summation x whole square. So this is the square of 836 for sample number 1, and this is the square of 794 for sample number 2. This is the square of 786 for sample number 3. This is the square of 754 for sample number 4. And then we have the summation x square, which are the sum of the squares of individual observations that we calculated from the previous table. So this is 70,036 for sample number 1, 63,100 for sample number 2, 61,878 for sample number 3, and 57,006 for sample number 4. And the total is 252,020. So you can see that there is a difference between the summation x whole square and the summation x square. The summation x square, which is presented in the last row, is the sum of the individual the square values of the individual observations, right? Individual square values. While summation x whole square, which is given in the second last row, is the square of the sum of observations for each sample, right? So first we take the sum, and then we take the square of that sum. And in the other case, we first take the square values of the individual observations, and then we take the sum of those individual square values. And you can see that these two values are different. Like for sample number 1, the summation x whole square is 698,896, while for the sample number 1, the summation x square is much lower. It is 70,036, right? For sample number 2, the summation x whole square is 630,436, and the summation x square is 63,100, and so on, right? So these are the descriptive statistics value that we have. We are going to use them for the ANOVA calculation. Now the ANOVA computation. So step number 1 is make a table of descriptive statistics. So we have already made that table, as we saw in the previous slide, that we have made the table of descriptive statistics. And what is step number 2? Test for the homogeneity of variance, right? And for that purpose we have to apply the F test. And the F test that we are going to use in this case is the F max test, right? So this is largest variance divided by smallest variance. In this case, the largest variance is 17.14 and the smallest variance is 6.25, and their variance ratio is 2.74. Now we have to consult the F max distribution table to see if this calculated value of the F max is significant or no. And for that purpose, we need to have information of two values, A value and V value. A is the number of samples or the treatments, which in this case is 4, and V is the degree of freedom of every sample or the smallest sample. So in this case, we have the number of observations same in all of the samples. But if we have the number of observations different in different samples, then V is going to be that degree of freedom which is of smallest sample, right? So let's suppose we have 3 samples of the number of observations 10, 9, and 8. So 8 is the smallest number of observations. So degree of freedom of this sample is going to be taken here, which is 7. But in this case, the example of the masses of starling that we are following, so in that case, the number of observations are same for every sample, which is 10. So our degree of freedom in this case is going to be 9. So 4 is our number of samples, and 9 is the degree of freedom for every sample. So what is the value here? The value is 6.31. So this is the tabled value. Now the calculated value is 2.74 and the table value is 6.31 at A4 and B9. So variances are homogeneous. We proceed with ANOVA, right? So we are good to proceed for ANOVA because their variances are homogeneous. So moving on to the step number 3, which is to calculate the correction term CT. So remember the formula for correction term. So correction term is summation xt, which is the total whole square divided by total number of observations. So this is 3170 square divided by 40, and the answer is 251,222.5. So this is the answer that we have for the correction term. Then in step number 4, we have to calculate the total sum of squares. So remember the ANOVA results table that we discussed. So what did we have in that ANOVA results table? We had to calculate the sum of squares, we had to calculate the degrees of freedom, and then we have to calculate the variances, and we had to calculate the F value. So right now we are calculating the sum of squares. And how many types of the sum of squares we needed to calculate? We needed to calculate 3 types of sum of squares: the total sum of squares, within samples sum of squares, and between samples sum of squares, right? So our next step is to calculate the total sum of squares here. So total sum of squares, this is the formula for the sum of squares. Remember I told you the formula before. So summation x square minus summation x whole square divided by n. So the total sum of squares that we calculate from here is 797.5, right? 797.5. So where do we get the value of summation x square? Remember we made the table for the descriptive statistics, so we had put down the value of summation x square over there, right? So this is 797.5. Now our step number 5 is to calculate the sum of squares between samples, and this is the formula for the calculation of sum of squares between samples. So here you can see that we have one factor for each of the samples, and then their sum is to be divided, is to be subtracted by the correction term. So first of all we have summation x1 whole square divided by n1, then we have summation x2 whole square divided by n2, then we have summation x3 whole square divided by n3, and then we have summation x4 whole square divided by n4. So we are putting in the values, and we are going to have the sum of squares, which is 341.9 for between samples, right? So this is how we calculate it. So this is a simple calculation. So first of all you have to calculate the summation x whole square by the number of observations for each of the samples. Then you have to take the sum of those individual values, and then you have to subtract them from the correction term, and you have your sum of squares between 341.9. So now you have calculated 2 sum of squares. We have calculated the sum of squares total, and we have calculated the sum of squares between. Now it is time for the third and the last sum of squares, which is sum of squares within. For that purpose we have to calculate the individual sum of squares of all the 4 samples. So sum of squares within for sample number 1, and this is the formula, and we have 146.4. Then sum of squares for sample number 2, 56.4. So you see, we have put all these things into our descriptive table first. So once you have made your descriptive table, after that it is very easy to do the ANOVA. You just have to remember that what you have to calculate. There is a general formula for calculating the sum of squares, and you have to memorize that formula, and it's easy for you then, right? So you have to calculate 3 types of the sum of squares, and you have to calculate 3 types of the degrees of freedom. You have to calculate 2 types of variances. That's it. And then in the end you have to calculate the F value. So the sum of squares for the 3rd sample is 98.4, and the sum of squares for the 4th sample is 154.4. So here you have the total sum of squares within, and this is 455.6, right? Step number 7 is you can cross-check the value of sum of squares within, because the total sum of squares is equal to sum of squares between plus sum of squares within, because remember, the total variability is equal to variability between samples and variability within samples. So the total sum of squares is equal to the sum of squares between samples and the sum of squares within samples. So if we have calculated 2 of these values, we can work out the value of the 3rd one. So the sum of squares within is equal to sum of squares total minus sum of squares between. So this should be 797.5 minus 341.9, and the answer is same, 455.6. So this is a cross check that you have done the calculations correctly. Now in the next step, you have to determine the number of degrees of freedom for each sum of squares. So good thing is that you're done with the column number 1, which is the calculation of sum of squares. Now it is time for the calculation of column number 2, which is the degree of freedom for each of these 3 sources of variation. So degree of freedom for the total sum of squares is the total number of observations minus 1, because we are talking about total, so we are talking about the total number of observations. In this case, this is 40, and this is 40 minus 1, and this is 39. So degree of freedom for SS between is A minus 1. A is, remember, A is the number of samples. So A minus 1 is 4 minus 1, so this is equal to 3. And the degree of freedom for SS within is the total number of observations minus A, right? 40 minus 4, or 30, it is 36. Or you can calculate the individual degrees of freedom for each of the samples. Like degree of freedom for the sample number 1 is 9, for sample number 2 is 9, for sample number 3 is 9, and for sample number 4 is also 9. And then you can take their sum, that is also 36. But this is a right way to do this, because every time you have every time you don't have the same number of observations in each of the samples. So to avoid that confusion, you just take the total number of observations and subtract the number of classes or the number of samples from them, not the number of classes, the number of samples, and you will have your degree of freedom for within, right? So you have now calculated the degrees of freedom for all the 3 sources of variation. Now it is time to estimate the variances, and remember, we need to calculate variance for between samples and within samples. So this is the formula for the variance between the samples. So SS between, that you have already calculated, and the degree of freedom between, that you have already calculated as well. So this is simply the sum of squares divided by the degree of freedom, and you have your value, which is 341.9 divided by 3, and the answer is 113.97. And then for the sum of squares within, you have again that simple formula, the sum of squares divided by the degree of freedom. So this is 455.6 divided by 36, which is the degree of freedom for the within sum of squares. So here is your answer, which is 12.66. So now you have calculated your 3rd column of the ANOVA table as well, that you are done with the calculation of variances as well. What is the next step? The next step is to compute the F value. This is not the F max, this is the F value, which is actually the value of ANOVA. And the formula is between samples variance divided by within samples variance, or this is in terms of the symbols, this is S square between divided by S square within, right? So now you have calculated the variances as well. In the previous slide you saw that we have calculated the between samples variance as well as the within samples variance. So we are putting in the values 113.97 divided by 12.66, and the answer is 9.002. So finally you have your answer. This is your answer of ANOVA, right? This is your test statistic for ANOVA. Now, one point to remember in this case is because the denominator is always within samples variance, right? Or in other words, we can say the numerator is always the between samples variance. So therefore, the f-test is one-tailed because we are always taking denominator as within samples variance. So remember in the previous cases that we had the f-test in which we were dividing the greater variance by the lesser variance, and we were not nominating any of the samples, right, to be denominator or any of the samples to be nominator. So any sample that has got the greater variance is numerator, and any of the samples that has got the lesser variance is denominator. But in this case we are not considering the values of their variances, rather we are considering their type, that within samples variance, whether this is small or this is greater, this is always going to be the denominator. Therefore, the f-test in this case is one-tailed. Therefore, we are going to use a separate table of f-distribution for that purpose. And this is the table. So, because we compared the ratio of the between samples variance and the within samples variance, so we are going to consider their degrees of freedom. So degree of freedom for between is 3 and the degree of freedom for within is 36. So we are going to check the value at 3 and 36 degrees of freedom, and that value is 2.87. Similarly, we check the f values for the 0.01 and 0.001 levels. And now we compare the calculated f value with the tabled f value, and we find that our null hypothesis is rejected. So our next step is to construct the ANOVA summary table, and here we are with the table, and you can see that we have all the values that we calculated put in here, and the sum of squares for between samples is 341.9, sum of squares for within samples is 455.6, sum of squares for total is 797.5. The degree of freedom for between is 3, and degree of freedom for within samples is 36, and the total degree of freedom is 39. The variance for between samples is 113.97, and the variance for within samples is 12.66. And the variance ratio, f value here, is 9.002, and the probability is very highly significant. So we state our result that the difference in mean mass of starlings from 4 different roosting places is very highly significant, right? So this is our result. So when we do ANOVA through some software, so we are going to have the ANOVA summary or the ANOVA results table in this form. So you can see that this is the same type of the table that we calculated through the manual calculations. And the source of variation is treatment. Treatment means between groups, and the error means within samples, and then we have the total. So these are the same values that we calculated. And here you can see that instead of variance, the word ms is written. So some of the softwares, they give you the result by stating the value of ms. So what is ms? It is the mean sum of squares, which is nothing but variance, right? So variance is also known as the mean sum of squares. So there is nothing to worry about if you do the ANOVA computation on a software, that what is this ms that you're getting. This ms is actually the variance value, right? And the f value is also the same. This is 9.01. And you also don't have to be afraid of these two terms, error and treatment. Error is nothing. This is within samples variance, and treatment is your samples or your groups. So this is between groups variance or between groups, between samples variance. So this is how we do ANOVA.